Okay, this is video 2 for the mechanical waves unit. To start off with this one, we're going to talk about the Doppler effect. Um, the observed frequency of a wave depends on the relative motion of the source and observer. And we're only going to do this qualitatively. We're not going to do any math with this one. So if there's something that makes sound, such as an ambulance, think maybe a boat out in the water, um, screaming child, whatever you want to do, something that's making waves. If that object is moving, it actually influences the frequency. So here we have an object that's moving, and this is an object creating sound. Now this right here, this is called a wave front diagram. In this diagram, the lines here represent the crest, and the empty space in between represents the troughs. So we can have a transverse wave like this. And notice that when an object's moving, the waves in front of the object, it causes the wavelengths to become shorter. Now, the speed of the wave remains constant. So when we look at our formula for the speed of a wave, if, and again, waves typically travel at a constant velocity, when the wavelength goes down, the frequency must go up. So when it comes to sound, a higher frequency means a higher pitch. So think of someone talking very high. A lower frequency, so on this side, a longer wavelength. So if the wavelength goes up, the frequency must go down. A longer wavelength means a lower frequency, which is a lower pitch. I've got a demonstration. I'll show this to you in class. But it's a really cool phenomenon. I'm sure you guys have all experienced this. A police car with a siren's on drives past you. You can hear the pitch rise, and specifically, you can hear the pitch drop as the car passes you. Now, we're not going to do any math with it, but this is the model for the Doppler effect. And I'd like just for you to see it. We might run through some problems in class just to get an idea for how to use it. But it's a pretty simple equation. Now, where the Doppler effect is really useful is in astronomy, because light is a wave. So light has to obey the Doppler effect. So let's say we have a star that's moving, and the star is producing light. So here, right here we have our star, and the star is moving. The wavelengths of the light in front of the star should be getting shorter, which means the frequency should go up. And behind the star, the wavelengths should be stretched out, so the frequency should drop. We should see a noticeable change in that. So we have this blue shift and we have this red shift, but it's kind of hard to see what that means. We have an acronym called Roy G. Biv. It stands for red, orange, yellow, green, blue, indigo, violet. And really what this means is as you go from red to blue, the frequency increases. So higher frequency, shorter wavelength. So when I say a blue shift, what I mean is as the star is moving, the wavelengths are getting shorter, so the light becomes more of a bluish color. So that's this part, this side of the spectrum right here. When we see a red shift, that means that the wavelengths are being stretched out and the frequency is getting lower, and the color of the light's becoming more of this red, orangish yellow color. So using this and our model up here, if astronomers know this, and if astronomers know the speed of the wave, which is the speed of light, they can get a pretty good idea for the speed of the star. And we can also tell whether the stars coming at us are going away. Okay, the next topic is superposition. Let's say we have two wave pulses, and let's say that they collide. What's going to happen? Well, it's counterintuitive, but they pass through each other. But as they're passing through each other, their amplitudes will interact, and we call this interference. So the first type is constructive interference. So here we have two positive wave pulses, and as they come together, their amplitudes add. So in other words, if A is 3 and B is 4, A plus B would be 7. Then they would go through each other and go away like nothing ever happened. Destructive interference is sort of the same thing, except that, let's say A is positive 3 and B is negative 3. Well, positive 3 minus 3 gives us 0. And then the waves will then go away like nothing ever happened. I'll show you some animations for this. It's really, really kind of cool. If you were to pause the film where it's just a straight line and then play it from there, it's like two waves erupt out of nothing. But we have this positive and, or this constructive and destructive interference. And the destructive interference, this is called complete destructive interference, because A plus B equals 0. It's not always going to be that way. If we're talking in terms of sound, let's say if two sound waves are having constructive interference, their volume will get louder. Okay? For destructive interference between two sound waves, the volume would get quieter. So we have an interesting case here where we can have sound plus sound equaling silence. In terms of light, constructive interference means that two light pulses, when they constructively interfere, they become brighter. Or if they destructively interfere, they can become dimmer. So again, think about it this way. Light plus light equals darkness. And that's a really, really cool thing to think about. Now, using this then, let's say we have a wave pulse on a string, and we let it encounter different kinds of boundaries. So first off, we have the fixed end. So we have our wave pulse coming. When it encounters the fixed end, its amplitude switches, and it goes back as a negative amplitude. If we have a movable end, such as this one, as the wave encounters this ring will pick up and then go back down, and then the wave will be sent back on the same side. So if it comes in as a positive amplitude, it will leave as a positive amplitude. If I have a wave pulse that goes from a light string, so less dense, to a more dense string, here we have it coming as a positive amplitude. It's going to send a small positive amplitude through the more dense, but then as part of that wave is going to reflect as a negative amplitude, kind of like it's hitting a fixed end. If I have, let's say maybe going from a light, a heavy string to a light string, such as this one, it's going to send positive amplitude, and then it's going to have a reflection as well. And there's different things that we can do with this. Now let's say we have actual waves, and let's say we have two traveling waves. Well, what can happen is that they can interfere with each other. Excuse me. So let's say we have two water waves. Excuse me. And these two water waves are at 2 points. So here I have one up here, and here I have one here. And it's from these two people fishing. If these two periodic waves, that means that it's constantly bobbing, sending out ripples. If these waves are of the same amplitude and the same frequency, we can have something really, really interesting happening. We can have some constructive and destructive interference. We can see it a little bit here, but I think this picture down here makes it a little nicer to see. So imagine that these are those two bobbers right here and right here. And as they interact, notice that we get these regions of constructive interference. But we also get these regions of destructive interference. This is true for all waves. Sound, light, doesn't matter. It's true for all waves. So if this were, let's say, two speakers, if you were to put your ear right here, you would hear nothing. If you were to put your ear here, you would hear a louder sound. Loud, nothing, loud. If these were two laser beams, so two sources of light, we would see that we would have bright and dark patches. Again, sound plus sound equaling silence, and light plus light equaling darkness. In these examples, the two waves must have the same frequency. If they have different frequencies, you will not observe this phenomenon, not the same way that you would think. So what would happen if they do have different waves or different frequencies? That's where we get something called beats. So here I have two waves with the same amplitude, but slightly different frequencies. What I get is regions of constructive interference and regions of destructive interference. Musicians use this when we tune our instruments. We have two instruments that we're trying to tune. And what we would hear is kind of like this wah, 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 wah kind of sound, where we'd have the constructive and the destructive. And basically, to find out the beats, you just do subtraction. So let's say I have the first wave has a frequency of 10 hertz. And let's say the second wave has a frequency of 12 hertz. We would just simply subtract it, and we would get a beat pattern of 2 hertz. In other words, we would hear 2 beats per second. If I have something, let's say 30 hertz and 40 hertz, I would hear a beat pattern of 10 hertz. I would hear 10 beats per second. And again, I have some demonstrations where I can show that to you in the classroom. All right, that concludes this section of the notes.